So in this video, the quantum numbers, we're going to start to think about where's the electron and how do we describe where it could be, since we just learned that we don't know where exactly it is. So how does that work? So we never know exactly where it is, but we're going to start to think about likely locations. So Schrodinger developed an equation to describe the likely places where it could be. So this here is the Schrodinger equation where H psi equals E psi. Now, we might look at this and think, you could just cancel those two psi molecules and then H would equal E. It turns out that it doesn't quite work that way. So H and E are mathematical operators. Which basically means it's a complex equation. And psi is called the wave function. And so this is the wave nature of an electron. So H times psi gives us information that accounts for both the particle and wave nature. So when we think about the wave function, we're going to look at several wave functions. We're going to look at the results, not the mathematical formula. So the wave function itself is not meaningless, but alone it doesn't tell us much. However, psi squared, or the squaring of the wave function, gives us a probability distribution. This basically says we are most likely to find an electron here. What does it mean when it's there? We're going to find out. So within these equations, there are these things called quantum numbers that identify the possible locations for an electron. And there are several of them. So in this equation, each orbital is described with 3 quantum numbers. So these 3 are used to describe orbitals. All 4 of these are an electron in an orbital. So the first one is the N principal quantum number. So this is the first N. L is the angular quantum number, followed by M sub L, which is the magnetic quantum number, and M sub S, the spin quantum numbers. So there are 4 numbers that we are going to use in order to describe the location of any electron. So let's look at each one of these individually. So the principal quantum number, this determines the distance from the nucleus. So if we were to think about this, we are saying, okay, the electron could be here, 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 or here. And those lines are the orbitals that came from the Bohr postulates. So the allowed values for N are not 0 to infinity. They are, in fact, 1 to infinity, as your slides are going to show. So these are the allowed values. It turns out that we can calculate using this equation where the energy at any state is negative 2.18 times 10 to the negative 18 joules multiplied by 1 over n squared. So if we were to look at these, where we have increasing energy, we could plug in different values for n equals 1. Then we're going to get n equals 2, n equals 3, 4, 5, 6, 7. So we can see these states and they order from bottom to top in increasing n values. But if the nucleus is here, they get further and further away from the nucleus, but at higher n values, they get closer together. So this tells us that we are going to see different energy states based on the principal quantum number. So the n value tells you how far it is from the nucleus. So the angular momentum quantum number, L, determines the shape of the orbital. So the allowed values for L are 0 all the way up to n minus 1. So for n equals 1, the allowed value is 0. For n equals 3, it is L equals 0, 1, or 2. So this is the allowed value. If we are giving the address of an electron, it can only have 1. So any specific orbital can only have 1 L value. There are standard L values. So for the s orbital, L equals 1, L equals 0. For p, L equals 1, d, L equals 2, f, L equals 3. We can predict mathematically that there should be a G and H orbital. But we haven't observed those either through different types of spectroscopy or located electrons that live there. But mathematically, there are solutions to the Schrodinger equation using values other than 0 through 3. So the next quantum number, the magnetic quantum number, is going to tell us where the electron lives within any of these values. So M sub L specifies the orientation of an orbital. In the video after this, we will look at more information about that. So the allowed values are negative L through 0 to L. So for L equals 1, it gives you, for in this case, it's a p orbital, you get M sub L is equal to negative 1, 0, and 1. For L equals 5, which is a unidentified orbital, you would get negative 5, negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, and 5. So there are a lot more options the greater your L value is. The M sub L value tells you about the uniqueness of each orbital. So together, N, L, and M sub L tells you that the electron could be in one of 3 p orbitals or 5 d orbitals. So M sub s is going to specify the orientation of an electron within a specific orbital. And the allowed values are plus 1/2 and minus 1/2. In the next set of videos, so video set 9, we will talk about when and how the different values change. But what we need to know is that there are only 2 different options, plus 1/2 and minus 1/2. It can only be either one of those. An electron can't be in 2 places at once. So some quantum number summary items. The number of sublevels, so these are the L values, L values, is equal to n. The number of orbitals, so the number of M sub L options, is equal to 2L plus 1. And the total number of orbitals in a level is equal to n squared. So let's look at the different energy states of several different values. So if we have our n states, so if we have n equals 1, if we know that n equals 1, and I actually want to move this over here so that it'll look funner. So n equals 1, therefore L equals 0, because it has to. M sub L, the allowed value, is also 0. So this is going to be the 1s orbital. So let's look at the n equals 2 values. So if we have n equals 2, for the allowed L values, there is both 0 and 1. So we have L equals 0, which gives me M sub L, also equal to 0. So this is going to be the 2s. But we also see the p orbitals show up. So n equals 2, L equals 1, M sub L equals negative 1, 0, and 1. So there are 3p orbitals, and those 3p orbitals go in 3 different orientations. So an electron could be in any one of these. So let's look at the 3, or at the n equals 3. So we have n equals 3, L equals 0, m sub L equals 0. This gives us the 3s. We have this similar situation for the 3p, where n equals 3, L equals 1, m sub L equals -1, 0, and 1. But when n equals 3 and L equals 2, m sub L is going to be equal to -2, -1, 0, 1, and 2. Oops. So there are 5 d orbitals. And so we will look at where these are located in the periodic table in later videos, but we can describe these locations using the quantum numbers. So this table might be helpful to look at the different values as well as what they are. This is just a summary. So let's look at some examples. So what are the possible m sub L values for L equals 5? So m sub L equals -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5. Or -L through 0 to +L. Keep in mind that an electron can only be in one location. It cannot be in all of these different orbitals. So m sub L for L equals 2 is -2, -1, 0, 1, and 2. So the L values, in this case, we're looking at the different d orbitals. So let's look at another example. So what are the possible L values for these 3 different n values? So for n equals 2, L equals 0 and 1. For n equals 5, L equals 0, 1, 2, 3, and 4. For n equals 9, we have L equals 0, 1, 2, 3, 4, 5, 6, 7, and 8. So what we see here is that n can be any, L for any value of n is 0 all the way up to n minus 1. So the other way that we'll think about quantum numbers is to ask ourselves which of the following sets of quantum numbers either is valid or is not valid. So which of these is not valid? So in this case, we're asking ourselves, do any of the values not match the allowed values? So in the first one, if n equals 2, L equals 2, m sub L equals 0, and m sub S is 1/2. So the allowed values for L are 0 to 1 minus L, 1 minus n. So this first one is not allowed. But let's check the others. So if n equals 3 and L equals 1, that's an allowed value. M sub L is -1, also allowed. M sub S is plus 1/2. That looks good. So for the next one, n equals 2, good. L equals 1, an allowed value. M sub L equals 1, and M sub S is minus 1/2. Also good. For the last one, n equals 3, L equals 2, where this looks good. M sub L equals 3. If L equals 2, the allowed values are -L to +L. So that means this is also incorrect. So we can look at quantum numbers and ask, how do these interact based on one another? And in that case, you need to move from left to right to figure out, is it an allowed value of n? Does that L value correspond to a possible location? Is that m sub L allowed based on that L value? And is m sub S a single number? So let's think about electrons. So if we have these states, the electron can move between these states, and we've observed that based on the line spectra. So we can calculate the difference between these two states, where the change in energy is negative 2.18 times 10 to the negative 18 joules, multiplied by 1 over nf squared minus 1 over ni squared. So this is going to give us the change in energy for the atom. This is also going to be equal to negative E photon. So we can rearrange the energy of a photon equation that we learned about previously to solve for the wavelength of light. So let's think about what this means. So if we have n equals 1, 2, 3, 4, and 5. So if we have electrons that go up, it's going to be ionized, and it can leave. Or it could reach any of these states and then decay. So if all of them return to n equals 1, this is going to be in the UV light. So to return to n equals 1, we may or may not observe that. These returning to n equals 2, this is going to be visible. Or we can see infrared light at higher numbers. So for any of these lines, such as this one, this is the n equals 5 to n equals 1 transition. You could also write that of n, 5 to 1. Let me move that back over. So we could look at this for any of these, which means that we can calculate the wavelength of light that corresponds to this transition. So we could observe the visible, but based on what we know from thermochemistry, the energy allowed to promote this from 1 to 5 is going to be equal to the wavelength of light emitted. So let's look at some examples. So we want to determine the wavelength of light in nanometers emitted when an electron transitions from n equals 6 to n equals 5. So there are really no sig figs in this calculation, so we're going to go ahead and assign that we need to have 4 in our answer. So we know that this is going to be Ni, and this is Nf. So the change in energy is equal to negative 2.18 times 10 to the negative 18 joules, 1 over 5 squared minus 1 over 6 squared. And this equals negative 2.66 times 10 to the negative 20th joules. And this is going to be equal to negative E photon. So E photon will be positive. So lambda equals hc over E photon. So we can just plug in our values of 6.626 times 10 to the negative 34th joule seconds, multiplied by 2.998 times 10 to the 8th meters per second. Divide that by 2.66 times 10 to the negative 20th joules. It asks for it in nanometers, so we're going to go ahead and multiply by 1 times 10 to the 9th nanometers in 1 meter. And that's going to give us 7,468 nanometers. So that is not light that we can observe. But what we can see is that this light would be emitted during this transition. So let's look at one where it's going in the opposite direction. So what is the wavelength of light in nanometer absorbed when an electron is promoted from n equals 2 to n equals 7? Again, 4 sig figs. So NF is 7, and I is 2. So delta E is going to equal negative 2.18 times 10 to the negative 18 joules, 1 over 7 squared minus 1 over 2 squared, and that's going to equal 5.005 times 10 to the negative 19 joules. And it turns out that this equals E photon. So we know that the transition in an absorption in an absorption, the energy is put in, so we don't need to change the sign. So we can again calculate the wavelength of hc over E photon. When you plug all of these values in, you would get 3.969 times 10 to the negative 7th meters. It's asking for that in nanometers. So it would be 1 meter times 1 times 10 to the 9th nanometers. And that gives me 369.9 nanometers. So we can calculate the wavelength of light that corresponds to any transition. We can also assign the location of any electron with its quantum numbers.